Welcome to week 1 of Metrics and Statistics. This video we're going to take an introductory view of statistics, see what exactly statistics is, how it's made up, how we collect data for statistics, and then what types of data we can be collecting as we collect it. Now first, you'll probably want to know what is business statistics, because that's kind of the focus of this course, is how statistics can be applied in the business and economics world. Well, basically, business statistics is a collection of procedures and techniques that are used to convert data into meaningful information within the business environment. We live in a world where big data is easy to access, with the internet, with Amazon.com leading the way, with collecting data on everything customers do. You log into Amazon.com and it tells you, hey, based on what you've looked at and bought before, you're probably interested in this. And gee, that does look interesting. And you buy it. It's a great sales technique. Google is getting really good at this as well. Google can take a global picture of you based on what websites you visit using their browser, based on what emails you use using their email account, Gmail, based on the content of those emails, based on searches you've done on Google. Over time, it creates the statistical data package and it predicts what you want, to the point where you can log into Google and ask it, how do I build? And Google automatically fills in the rest for you, and half the time they already know what you're trying to build before you tried to build it. This is business statistics, using statistics to help your business be successful, either internally or externally. Lots of great things you can do and apply in this math class, which is why it's one of my favorite math classes, because it's really a math class where you can see how you can use this in the real world. Now, statistics is really made up of 2 parts, and we're going to follow this pattern in this course. The first part will cover up to the midterm, and the second part will cover up to the final. The first part is called descriptive statistics. Now, descriptive statistics looks at data and tries to describe it in a meaningful way. We do this with charts. We do this with graphs, often bar graphs, line graphs, pie charts. We can also do this numerically, maybe with a mean or a median or a mode that tells you, well, the average salary for this community is. Well, the average number of widgets that don't work in this factory are. And we can figure out a representation of this large amount of data. That's descriptive statistics. We're describing the data. The second half of statistics is called inferential statistics, and this is where we do estimation and hypothesis testing. This is where we estimate what's going to happen. We estimate that the average person will supersize their meal this often. We estimate that this proportion of your employees are satisfied with their work environment. There's also hypothesis testing, which takes a look at those estimations, or takes a look at those claims and says, are they true? Are they accurate? Do we have enough statistical data to verify this claim that's being made? Is Coke better than Pepsi? Do 4 out of 5 dentists recommend Colgate? Is that accurate? So here's an example of some descriptive statistics. This is just a simple chart that shows 3 companies, XYZ, ABC, and PQR, and kind of what their sales are doing in the first quarter of the year. And you can see, well, the red line, ABC, they're a smaller business, but they're getting better. And we see the gray line, PQR, the big business, is kind of going downhill. And so you can make some conclusions based on this descriptive picture of the statistics of the sales for the past 3 months. Here's another example of statistics. Median household income in the state of Washington between 2007 and 2011 was $58,890. That's a descriptive statistic. It describes the people in the state of Washington. On the other side, we have our inferential statistics. Now, inferential statistics are going to make a claim or an estimation. So on August 23rd of 2013, Gallup organization went out and surveyed a bunch of people and determined that underemployment, people who work part-time but want to work full-time, was at about 17.8%, with a margin of error of 5 plus or minus 5%, which means it could be as low as 12.8 or as high as 22.8%. We are estimating the underemployment to be around that number. And the reason we have to estimate is it's impossible to ask every single person in the world, or at least in the United States in this case, do you have a part-time job? Do you want to be full-time? That takes a lot of money and a lot of time. So we do a small sample, and we estimate for everybody in the population. And we have a margin of error in that estimation because we didn't interview everybody. And that gives us what's called a confidence interval that's somewhere between 12.8 and 22.8% of people are underemployed. Also, hypothesis testing happens in inferential statistics, where we'll make some type of claim. People prefer Coke over Pepsi. And so we'll make a hypothesis that there's no difference, actually, in people's preferences. And the burden of proof, if you will, to use court lingo, the burden of proof is to prove that is false. And so we'll do a test to see if there is a significant difference in opinion. And the survey results come in, and we either say, wow, people really do prefer Coke over Pepsi. And so we have to reject the hypothesis and say there is a difference. Or maybe the information comes in and there's not a significant difference. Boy, the survey shows people really don't have a preference overall. And so we will fail to reject the hypothesis. There's no proof that there is a difference in people's preference. Now, in order to do either inferential or descriptive statistics, we do have to collect data to be able to make these predictions or make these conclusions. Now, there are several ways we can do that. One is to make up some type of experiment, some type of process to produce an outcome where the result cannot be predicted with certainty. For example, Simplot makes French fries. They make most of the French fries for the Northwest, for Burger King, McDonald's, Wendy's. They all come out of the same plant. But they have to decide how long to blanch the fry and at what temperature to blanch the fry so that the French fries in Spokane are the same as the French fries in Seattle. Different batches, so we need to make sure they are done correctly. And so we might make a table of values that shows, hey, let's test a few. So let's test them. Let's blanch them at lots of different temperatures and record what happens. And that's our data from the experiment. There's another way to collect data too, and this is a very common way. You've probably have some experience with telephone surveys. You get a phone call, hey, would you mind to take a few minutes, answer a few questions about our product, answer a few questions about your political views, who are you going to vote for, are you going to vote? These surveys are done all the time. The trick is, because you're taking up people's valuable time, you need to have very short, closed-end questions, and this limits the types of responses you get. You can't ask people, what are your political beliefs? You have to ask, to what political party do you belong? Republican, Democrat, or other? They can give a quick answer, and you can move on. You probably won't have more than 2 or 3 minutes to conduct a survey by phone. It's also important that you beware of the wording and tone of your questions that might introduce bias. In this previous example, you might have to change up the question every time you ask it. Half of the people are asked, are you a Republican, Democrat, or other? The other half are asked, are you a Democrat, Republican, or other? Notice switching the order of the question reduces the bias of putting Republican first for every responder. It's also difficult to reach a broad range of responders with a telephone survey. Some people aren't home in the evenings, so they're automatically excluded from the survey, but yet their information may be very valuable to the results of the data. Another method often used for data collection are written surveys and written questionnaires. These are either mailed or they're handed to you as you walk in the door or out the door of an event. I go to many conferences, and every conference, at the end of the conference, they give us an evaluation that we need to fill out as we leave so they know what we thought of the conference. The trick with these is you have to make sure they look very professional. If they don't look professionally created, with a clear header, with nice typeface, organized, they're not going to be filled out because people won't take them seriously. You also have to be aware of leading questions. Same with telephone interviews. If you ask people, to what extent would you support paying a small increase in taxes if it allows poor and disadvantaged children food and shelter? Well, who doesn't want to help poor and disadvantaged children? Who's going to say no to that? Now, if you ask them, do you want to increase taxes for social services? Now it removes that bias, and so there's not going to change people's opinions. We also have to be aware of poorly worded questions. One poorly worded question is, based on this sample, we give you a product. New food we're creating. New type of candy. We want to see if the kids like this candy, if they're going to eat it. So we're going to ask them to rate their preference of the taste and freshness on a scale of 1 to 10. Well, here's the problem. Is 1 good or bad? Is 10 good or bad? How is the scale set up? As soon as you read that, you made an assumption. You might have assumed 1 was good, or you might have assumed 10 was good, and 1 was bad. But it might not be what I, the survey collector, wants to see. It might be the opposite, and that's going to skew my data. Another problem with this question is they're asked to rate 2 different things with 1 number. They're asked to rate taste, and they're asked to rate freshness. It might taste really bad, but it's really fresh. So is that a 5? This really should be broken into 2 questions and clarifying, is a 1 good or is a 1 bad? Another type of data collection that's used is direct observation. You might work for a store and you want to change your storefront. Maybe change the colors of the sign, put different products out front. You want to know, how do the customers respond? Was this a good change or was it a bad change? And we should change it back to the way it was before the change. Now, when you're collecting data, there are a few issues to be aware of, to be careful of. The first issue is data accuracy. It's very common when people want some data. Now they just go on the internet and they download the first piece of data they can find on people's preference for fast food restaurants. The problem is you have to really consider what the source is. Where did the source come from? Did they interview people as they were leaving McDonald's? What their preference was in fast food restaurant? It might not be very accurate. We already talked about some bias with tone of question. Is the interviewer asking, what are your preferences on vehicle choice? Do you think this vehicle is comfortable to drive? Well, gee, that kind of rated a little low. Let me point out the features of this car. Now, do you want to readjust your answer? Ooh, that's some bias. Your survey is going to be changed. There's also a non-response bias. If you want to interview your employees and you want to get their view of how satisfied they are with the work environment, and you only interview the day crew, you're not going to get any response from the night crew unless they come in outside of their normal working hours. That's a problem because those night shifts might have some issues that your HR office needs to be aware of. I also referred to the selection bias. If we ask McDonald's customer their favorite fast food restaurant, it's not going to give us a good view of what people believe is the best restaurant. Another problem with observers, recording data is the observer often has a bias. If I'm watching a way a child interacts with a parent, and I believe this parent should not keep this child, I'm a social worker, I believe this child needs to be placed in an adoptive home that's going to be more supportive, I'm going to see a lot of problems with how the mother interacts with the child. Versus if I'm representing the mother and I want her to keep the child, I'm going to see all the positive interactions and I'll ignore what I don't want to see. And so that bias can definitely influence the results of your data. There's also an issue with measurement error. If you're running an experiment and you want to see how long are these boards when they come out of the conveyor belt. Are they all the correct size, or do we need to send them back? Is there a problem with our machinery? Well, if I want to measure them and I only measure them and put a clamp on them that just barely touches the edge, I'll get one type of measurement. Or I could tighten that clamp down real good, and that's going to make the board seem smaller. And that gives us a large variability in our results because of the inaccurate methods of measuring. So definitely need to be aware of how was the data collected. Is it accurate? Now, when we collect data, it's important that we know the difference between these two groups. We're going to use these terms a lot in this course, and we need to make sure we're using the correct term to talk about the correct group. There is a difference between a population and a difference between a sample. A population is the set of all objects or all individuals. Earlier we saw the median household income in the state of Washington. That is a population. We're talking about everybody in the state of Washington. Now, that's different than a sample, which we take a subset of the population. We take a small group to represent everybody. Now, that is like the Gallup poll that we saw that had the underemployment rate. We didn't interview everybody in the United States. We just took a small sample, a subset, and made assumptions about the entire population. So just to kind of clarify the difference between population and sample, we already talked about the population is everyone. The sample is some of them, hopefully a representative group. Now, each group has its own advantage, which is why sometimes we look at one and sometimes we look at the other. The advantage of the population is it's going to be very accurate. We are going to know if we take a survey of everyone exactly what the median income is. A sample is not going to be accurate. You're going to have a margin of error, and we'll talk about this in the second half of the course when we get to inferential statistics. But the advantage is cost and time, and often you hear the phrase time is money. So there's big cost savings in a sample because it's a lot easier. If I have 300 employees, it's a lot easier to interview only 30 or 40 of them and make conclusions than it is to interview all of them. Now, when we're describing a population in a sample, we'll use some variables to represent them. So when we talk about a population, we talk about what are called parameters. A population parameter, the average number of people per household, the average number of televisions per household, the average number of cell phones per household. All of these things are parameters because they are talking about everybody in the population. Now, if we say we took a sample and found out that on average there were this many cell phones per household, those are what are called statistics. Statistics come from small samples. Parameters come from the entire population. And to make it clear when we're reporting our data which group we're talking about, we're going to use different symbols. For populations, we use Greek symbols. These Greek letters here are mu and sigma. When you see a Greek letter, we know we're talking about everybody, the entire population. When we see an English letter, an alphanumeric letter, X or S, those are talking about just the small sample. And that way, when we're reporting our data, when we're talking about it in a paragraph reported to our manager or our supervisor. It's very clear what we measured and what we're doing with the data. Now, there are several sampling techniques we can use. When we're taking a sample to represent the entire population, the important thing about a sample is it must be random. And that's in quotes because random is really hard to define statistically. But it needs to be random and represent basically every group of the population at the correct level. There's lots of ways to do this, and you're going to get a chance in your Excel project for this week to play with different types of selecting random samples. A common sampling method is called simple random sampling. And this is where we assign each person a number. We might list them alphabetically, and Adams is 1. Johnson after that, Zachariah after that. We list them alphabetically and assign each person a number. And then we have Excel or some other program create some random numbers. And so it creates 15 random numbers, and those 15 people are selected to fill out the survey or to be called for the telephone interview. That's the simple method. There's also what's called a stratified random sampling. And this is where we divide a population into different subgroups and take samples of each subgroup. An example of this might be if we're looking at different financial institutions, and we want to know how many accounts each institution has. Well, there's a few really large banks that have most of the accounts. And so we want to make sure we take a sample of those few large banks, and then take a different sample of the few smaller banks. Maybe even have a group for medium-sized banks. And so we divide into the 3 subgroups, and then using a different method, maybe simple random sampling, take a portion of those each. Maybe we'll take 20 small banks, 5 medium banks, and 3 large banks. Another random sampling method is called the systematic random sampling. And this is where the sample is made up of every maybe 20th person, every 75th person, every 100th person to get the number we wanted. So if I have 200 employees and I want to systematically sample them, I might list them alphabetically because alphabetically should randomize the group. There's no pattern to people's last names usually, unless it's a family business. And then of these 200 employees, I want to interview 10 of them. Well, if I take every 20th person on the list, 200 divided by 10 is 20. If I take every 20th person on the list, that'll give me a fairly random sampling of the employees. Another way I could do this is I decide to do every 20th person. That would guarantee to leave out people at the beginning of the alphabet. So I create a random number between 1 and 20, and I get 7. So we do the 7th person, add 20, the 27th person, add 20, the 47th person, and that way everybody's got an equal chance of being picked in the systematic random sampling. A fourth method is called cluster sampling, and this kind of makes things a little more convenient, is you divide the population into many clusters and then select the clusters randomly. A good example of this would be if the Seattle Seahawks wanted to survey their customers, their fan base, or who they're selling their tickets to. It would take quite a while to walk around the entire stadium to random seat after random seat. However, the stadium is split up into sections. They could check how many sections they are, and maybe there's 150 sections in the seats. And they'll select 4 or 5 of them randomly and just give the survey to everybody in those sections. And that would make it easier to give out the survey because the people are all clustered together in the same place. That's cluster sampling. Now, once we sample and get our data, we need to know there are different types of data that they're going to be working with. First, The most common type you hear is quantitative data. That's data that's inherently numerical. It's something that you can measure. That idea of measurement is important. Quantitative is height, 5 foot 4 inches. Quantitative is the number of hours spent watching TV. That's a number that can be reported. Very clearly numerical. We can do things with it, find averages, add them together. That is quantitative. Salary, amount spent on salary for the company. Those are numbers. The other type of data is quantitative. This talks about the qualities of whatever you're surveying. It's inherently categorical. Some categories are color. What color car do you buy? That's red, blue, green. We can't get an average car color. That doesn't make sense. That's a category. That's quantitative. Marital status. Single, married, divorced, widowed. Those are qualities, quantitative categories. And you need to be very careful. A number doesn't necessarily mean it's quantitative. If you ask your customers to rate the service they've received on a scale of 1 to 5, where 1 is poor and 5 is very good. Well, 1 is a number, yes. But it's not quantitative. It's not inherently numerical. They're really talking about it being poor. They're talking about a category. So we need to make sure we're careful. Just because it's a number, does the number put them in categories, or is a number an actual measurement? Now, when we do take data, there are different levels of measurement that we can talk about. And the more complex your measurement system is, the more sophisticated statistical techniques we are going to need in order to collect data, or in order to make predictions with the data. So basically there's the scale from low to high, and there's 4 types of data we're going to talk about. There's nominal data, which is the most simple type, ordinal data, interval data, and ratio data, which is the most complex. Let's take a look at each of these and clearly define the different categories. First, nominal data. Nominal data is a category with no clear order. We're asking people, are you married, single, divorced, or other? Those are very clear categories that have no order. Because I could have asked, are you single, married, divorced, or other? Change the order. We'll get the same results. There's no order to these categories. This is nominal, qualitative data. In fact, those numbers don't mean much. We could have said 7 single, 12 married, -5 divorced, pi other. The numbers really don't mean anything in this nominal data. Because there's no order, there's no significance to that. We could have even used letters. S for single, M for married, D for divorced, O for other. No order. That's nominal data. Now there's ordinal data, which has some type of order to it. It is ranked categories. We have one that is bigger and one that is smaller. However, the spread between the categories is probably not the same. A common example of this is if you run a race, and there's the 5th place finisher and the 6th place finisher. The 5th place finisher was definitely ahead of the 6th place finisher. There's an order to them. It's different getting 6th place and 5th place. Now we have order. However, the spread is probably not the same. The amount of time between 5th and 6th place is probably different than the time between 4th and 5th place. So while we have order to 1st place, 2nd place, 3rd place, 4th place, there's not a difference of 3 seconds between each person. There's a clear order, but that's all we can do with it. We can't say the spread is this big. How far apart are 5th and 6th place? We don't know. It's just ordinal. There's just an order to the data. Which leads us to interval data. Interval data has a clear distance between the data values that can be measured. A is 5 more than B. These two data points are 5 apart from each other, and that space of 5 means something. The classic example here is temperature. 10 degrees or 20 degrees. It is 10 degrees yesterday, 20 degrees today. It is 10 degrees warmer. We have a set interval that a degree is this much space. The difference between 10 and 20 is the same as the difference between 20 and 30. But what's not here is the idea of 0. Now, yes, you can have 0 degrees, but 0 degrees does not mean no temperature. It's just another point on the scale. It's almost arbitrarily put on the scale. And because there's no real 0, we can't say 20 degrees is twice as warm as 10. That doesn't make any sense, because if you convert between Celsius and Fahrenheit, twice as warm is different because 0 is at different places. That's interval data. There's space between the numbers, but it's not necessarily on a true 0 scale. There's no starting point that means nothing. Which leads to ratio data, which has a true 0 data point that means nothing or none. Now we can use terms such as double, half. For example, one phone plan costs $20 a month. Another phone plan costs $40 a month. Regardless if we change this to a plan in euros, a plan in yen, a plan in German marks, the second plan will cost twice as much as the first plan, because there is a true 0 of $0 per month, meaning nothing. No phone plan if you pay $0 per month. So to kind of summarize what we've talked about in this introductory to stats video, we talked about statistics. It has two branches, descriptive and inferential. Descriptive describes data. Inferential makes hypothesis and estimations. Data can be collected in several methods: experiments, phone surveys, written questionnaires, direct observation. And when we collect data, we need to make sure we differentiate between a population and a sample. A population is everybody, a sample is a small portion. We talked about the difference between quantitative data and qualitative data. Quantitative data is inherently numerical and is measured. Qualitative data talks about the qualities, it's categorical. And then finally we talked about the different levels of data. Nominal data, which has no relationship to number or order, it's just categories. Ordinal data, which has order, one is more than the other. Interval data, when we put them in order, now there's a certain space between each of the intervals. And finally, ratio data, which has that true 0 point. Good luck on your homework assignment for this week. Let me know if you have any questions.